Good morning, everybody. Let's start our today's lecture. And first of all, I recall the basic definition from previous lecture. We had deal with so-called linear system of algebraic equation. What does mean linear system? Linear system is a collection of linear equation. Linear equation, the equation of following type. We have some collection of unknown variables, and these variables can be only a first degree in this equation. And geometrically, linear equation define some geometrical object in many-dimensional space, the same as a line and plane. For example, if n is equal to such equation defines in the plane straight line. In the case when we have n is equal to 3, such equation defines a plane in the geometrical space. We have some collect of such equation, and system define the system of such equation define intersection of such geometrical object. For example, if we have for example two equation, this linear system defines in the three-dimensional space intersection of plane, and this intersection can be either empty set, and if this intersection is known, empty, this intersection can be straight line or plane if two equations define the same plane, the equals planes. And our goal to solve this general type system. And the main idea is following. For example, if we have such system, for example, we have this system following type. For example, the basic simple idea expressed one of the variable in terms of other. For example, if we have such equation of two equation with two unknowns, we can, using second equation, express one of the variables, for example, x1 in terms of x2, and substitute this expression in the second in the second expression. We can, for example, I change the order equation. I use the following equation and I express the first unknown and substitute this expression in the second equation. And after substitution, we obtain the equation which contains only in our case only one unknown. And we can easily to solve the unknowns, and we obtain that this unknowns is equal 1 and substitute an expression which give us expression the first unknowns in terms of second, and we obtain the answer. X1 is equal 2, X2 is equal 1. In the case of such simple linear system, it's easy to solve such system. In general case, if we have enough many unknowns and many linear equations, we can also use the same approach and subsequently express, for example, first unknowns in term other and substitute another equation, and after that we obtain the linear system which has the order, the less order, so less than one order, and after them we repeat this this operation, and step by step we reduce our system to the one equation, and this equation can be now simple, and this equation can be has only one unknowns. In this case we obtain unique solution, and this equation can be consist of more than one unknowns, and in this case we obtain infinitely many solutions. And we have the following degenerate case. For example, easy to see this we have proportional left side and is not proportional right side. Easy to see if I multiply the first equation by 2, I obtain the equation which has the same left side and various right side, and this linear system is non-consistent. This linear system equivalent the following. And the second linear system hasn't unknowns, and the second equation is contradictory equality, and this equation no solution. And in the same way we can obtain such contradictory linear system. And we have three cases. First of all, the system has unique solution. Second case, the system has infinitely many solutions. And third case, the system has no solution. How to understand what the case we have in the any partial case? The main idea is following. The basic construction, the so-called reduced echelon form for linear system or matrix. Now convenient to use the so-called matrix formalism. We can consider matrix which contains the coefficients and the constant term of equation in the linear system. We write only coefficient. First of all, the first equation, and we also use the convenient formalism. We will use only one letter, A, for coefficients of equation of our linear system, and letter B for constant term in our linear equation. And we also use two indices. First of all, the index, the number of linear equation in which this coefficient, and second indexes, the number of the unknowns for these coefficients. And this matrix is called augmented matrix. And this matrix contains also constant terms. And matrix which contains only coefficients of linear equation is called coefficient matrix. And this matrix column, which contains only constant terms, is called constant matrix. And our term to solve this linear system, the equivalent way we want to simplify the matrix, augmented matrix, such a way that on the finite many steps we obtain the matrix which presents the solution. For example, what kind of matrix of our linear system present the solution. In these cases, matrix of following type: x1 is equal b1, x2 is equal b2, and xn is equal bn. We have the solution. The matrix which corresponds with solution has the following form: so-called identical matrix. And if we obtain this matrix, we solve our linear system. But in the case when our linear system has infinitely many solutions, the matrix which presents the solution has the other form. For example, x1 is equal b3, b3, b4, x4, x2 is equal b prime, 3x3, b tilde 4, x4. For example, this linear system is also present the solution, but in this case we have infinitely many solutions. What the matrix which presents such matrix has the following. For example, C1, C2. What the matrix has the following form: minus B3, minus B4, minus B prime, and in this case we have some collect of columns which present the identical matrix, and the other columns have the arbitrary form, and they have also constant term. And in this case we obtain also presentation of the solution of our system. And our goal to reduce the arbitrary matrix to one of the on this canonical form. What kind of operation can we use for such reducing? We have the three type such operation which not change the solution of linear system. If we have two linear systems which has the same solution, we say in this case that these two linear systems are equivalent in the sense that this linear system have the coincide the same solutions. This solution can be unique solution. Such of the solution have infinitely many partial solutions, and in this case we mean that every solution of first linear system also the solution the second, and any solution of second linear system also the solution of first linear system, and the sets of solutions are coincide. If we have S1, the set of solution of first linear system, and S2, the solution of the second linear system. What does mean that these sets are equal? It does mean that we have inclusion S1 is subset of S2 and S2 is subset of S1. What does it mean? This inclusion and this. If X is the element of S1, it follows X belongs S2. It doesn't mean exactly the first embedding. And the second, if X belongs S2, it follows X belongs S1. This is exact formulation of this inclusion using theoretical set language. And we have the case when each of this set is empty, and in this case we also obtain that this linear system are equivalent in the sense that this linear system has the same solution. This set can be empty. And what operation we can use for reducing the linear system to the more simple form? And we use the following three types of operation, and this operation we call elementary operation. I'm sorry. Okay.
When you wrote empty, called empty, you mean infinitely many solutions?
No. Empty set, the set which has no elements. Has no elements. For example, if we have the solution of this type 0 is equal non-zero element. For example, 0 is equal 1. Zero in the left side means we have some variables which has 0 coefficients, and in the right side we have arbitrary non-zero element.
So
yes, this solution has this equation has no solutions. We can substitute every numbers in the left side, and in every case we couldn't write equality. 0 is not equal 1. And we have no solution in this case. We have no solution. And in this case, we use the following notation: empty set. This set which has no element.
Yeah.
Mm-hmm.
And
Okay.
what does S mean? Some kind of coefficient?
No. We have the two linear system. One linear system and second linear system. And let S1, the set, is a set of solution. of solutions of first linear system. What does mean the solution? We have the solution, and let we have some n-tuple of integer, of some numbers, of real numbers, and this n-tuple is the solution if we substitute this solution as in the place of variables. We obtain the identity in we obtain the identity in the place of every equation. For example, x1 plus x2 is equal to. We can consider, for example, the two tuple 1, 1, and if you substitute this tuple in this equation, the first number, and we put the first variable, the first unknown x1 is equal to the first element of the two tuple, and the second we put is equal to the second element, we obtain the identity. And if we have such collection of numbers, and if we obtain after substitution in every equation identities, this n-tuple is called solution of our linear system. And we have, in this case, we have infinitely many solutions, this infinite set of solutions. And if we have two linear systems, what does it mean that this linear system are equivalent? By definition, we say that the two linear systems are equivalent if every solution, if the sets of solutions of these two linear systems are coincides. What does it mean? We have two arbitrary sets, A and B. What does it mean that two sets are coincide? By definition, it does mean if we have some element of the first set, this element also the element of the second set. Formally, from the fact that x belongs A, follows x the element of B. And this assertion is equivalent that A is subset B. And opposite assertion, if x is element B, it follows that x is element A. And we have opposite inclusion, B subset of A. And this assertion, does mean that two sets A and B are coincide by definition. And this set can be empty and this set can be empty. And in this case, two empty sets are coincide also. In this case, we have false assertion. We have no element which belongs A. But from false assertion follows any assertion, and this reduction is true. And this logical basic for our definition of and for our reasoning. Okay, yes, maybe questions. Yes.
Is the intersection of all of the answers the final answer is the intersection of all of the answers of the polynomials?
Repeat it. Intersection of what? Solutions?
S1, S2, S3.
S1. Yeah. Okay. Yes, you're right. If we have some collect of equation, for example, two equation, V1, and if S is a solution of this linear system, and we have also second linear equation, and this linear equation has a solution S prime. The solution of linear system is the intersection of solutions of every linear equation. Is true, but in this case, we consider the solution of all linear system, and it's true that the solution of linear system is intersection of solutions of every linear equation. Yes.
Thank you.
Yes. Very true. And okay, and I recall the definition of so-called reduced row echelon form. What does mean row echelon form? We have we can define remark that matrix, the augmented matrix is equivalent the linear system, and we will use matrix formalism for when we work with linear system. In this case, we do not write the unknowns and use only coefficients for our reasoning. For example, if we have the linear system, for example, such a linear system, we can use the matrix which equivalent this linear system. In this case, such matrix. This linear system and this matrix two type of language for description of the same object. This matrix unique way define the linear system, and we have linear system, we can write the corresponding matrix. And to solve the solution, equivalent to reduce this matrix to the canonical form. In our case, we reduced the matrix to this following form. And we can use the sum operation. What does mean to express one of the variable in terms of other? In our equation, we can use the following type of the operation. We can to add to arbitrary row other order which multiply on arbitrary number, and we can multiply any row on non-zero constant, and we can change the rows. We can change the place of the rows, and we use the following notation. By R we denote R with indexes. We denote the row of the matrix, and the first type of the operation can be written in the following form. We add to the row number I the row number G, which multiply on some constant lambda. The first type of the row operation. The second row we multiply some row on constant lambda, and in this case lambda is not equal 0. And second type, we change row number I and row number J. We have three types of rows. Example. We have our goal to exclude the first variable, to express the first variable in terms of the second. Each operation is equivalent to the following. We want to put the first variable equal 0, and we can subtract from second equation first equation. It does mean that we use the following operation. We can put the second row is equal second row plus minus 1 on the first row. And after this operation, the first row is not changed, but the second row, minus 1 times 1 plus 2 is equal 0. Minus 1 times minus 1, 1 plus 1 is equal 2. Minus 1 plus 3 is equal 2. And we obtain the following linear system. The next operation, we can multiply the second rows on half 1, the ratio 1, 2. And after this operation, the second row simplify and has the form 1, 1. And the last operation, we can add the second rows to the first. And after this operation, we obtain the final form of our matrix. On the left side, we have identical matrix, and in the constant column present the values of solution of our system. The coefficients for x1, 1, and this matrix equivalent the following linear system. x1 is equal to x2 is equal 1. And this linear system is a solution of our initial linear system. We obtain two equivalent augmented matrix. This augmented matrix and this are equivalent. And this augmented matrix present the most simple form of our linear system. This most simple form is a solution. And what this most simple form matrix is called reduced row echelon form. And now I try to define this most simple form of matrix which equivalent the solution. And our aim using this three type of operation reduce the arbitrary matrix to the reduced row echelon form. What does mean row echelon form? The definition of reduced echelon form. The reduced echelon form is defined by the following three properties. First property, if a row does not zero, does not consist entirely zeros, then the first non-zero element number in the row is a 1. This element is called leading. The first property. The second. if there are any rows that consist entire 0, then are grouped in the bottom of the matrix. If we have some matrix in row echelon form, the rows which consist only zeros are grouped in the bottom of the matrix. Second, in any two successive rows that do not consist entirely zeros. The leading term in the lower rows, the row occurs further to the right. Then the leading term in the higher row. What does mean the last property? If we have two successive rows in the matrix, we have two successive two rows in the matrix. In the maybe number of these rows I and the numbers of the second rows I plus 1, two successive rows. And in the first rows we have first non-zero element. By definition, this element is equal to 1. In the second row, the leading element also, which is equal to 1, lies rather right, relatively this element. If this element on the place number j, this element has the place numbers j plus, no, exactly 1, maybe 2, 3, only rather right. Example, echelon form. This most important properties in the echelon form. Example. Example echelon form. The first rows. First non-zero element is equal to 1 in the first place. Second row. The leading element 1, the place is equal to 3. 3 greater than 1. Third rows. The first non-zero element 1 is leading element and number 4. Number 4. Number of the place 4. And we have, in this case, echelon form. How they relate the echelon form with solution? Let we obtain some echelon form for augmented matrix. How to obtain the solution? How to obtain the solution from the echelon form? We can mark the rows which contains the leading element. Easy to see that there exists one column which contains the leading element of some rows. In our case, we have the first column, third column, and fourth column, and we have this leading element. This leading element corresponds to the unknowns x1, x3, and x4. Our goal to express this variable in terms of other variables. This unknown x1, x3, and x4 will play the role of dependent variables. The other variables, x2 and x5, will be independent variables. And our goal to express the dependent variables in the term of independent variables. How we can do this? How we can express these variables? What we can do with matrix if we want to express this variable? The goal is the following: to obtain, to reduce the matrix which contains the marked columns, reduced to the identical matrix. In this case, we obtain this expression. In our matrix, we have 0 elements which lies below of the leading element, but up elements is not 0. and our attempt to put this element equal 0 using the elementary operation. And in this place and in this place we want to put the 0 element. How to obtain the 0 in this place? We can subtract from second row, third rows, and in this case we obtain the 0 in this place. How to obtain in this place 0? We can use also the rows operation and subtract from first rows, second rows multiplying 2. Okay, and after this operation we obtain the reduced form with equivalent solution. And main remark, the reduced echelon form is very close to the form with equivalent solution. The solution will be easy to obtain from reduced echelon form using the same procedure. The first assertion: how to obtain the reduced row echelon form? We have the arbitrary matrix. How to obtain the row? We have two problems. First, how to obtain reduced row echelon form. How to obtain from row echelon form solution. Solution of our linear system. We have two problems. First, how to obtain echelon form, and second, how to obtain the solution. The answer is the same. We will use Gaussian elimination method. How to obtain the row echelon form? We have arbitrary augmented matrix of arbitrary linear system. The first step, let's consider the first element in the first row. The question: this element is not 0 or 0. We can suggest that this element is not 0. If this element is equal to 0, we can change these rows with rows when the first element is not 0. This 0, we look for the non-zero element in the second column. Let's sum element on the place number I is not equal 0. We change place these rows with this, using the third elementary operation. After them, we can suggest that this element is not 0. After them, we can divide this element. We can divide this first row on this element, and we can put R1 is equal 1 divided A1, 1, R1, and after them we obtain the following linear system. Next step. Our aim, our goal, to obtain the 0 on the other places in the first column. To transform this element in the zeros using elementary operation. How to do that? Easy to see. We can use the operation of the type 2. We can put Ri is equal Ri plus minus I R1. We add to these rows which multiply on the element opposite to this element. For example, we multiply the first row on the element minus A to 1 and plus to these rows. Minus A to 1 plus A to 1 is equal 0. And in this place, we obtain 0. We have the m minus 1 operation. R2 is equal R2 plus minus A to 1 R1. R3 is equal R3 plus minus A3 1 R1, and so on. Rm is equal M plus minus AM 1 R1. After applying this operation, we obtain the 0 in the first column, which lies below the leading element. We obtain the following form. and we obtain the matrix which has a following property. All elements in the second column, which lies below the leading element, are equal 0. And we reduce our problem to the problem for matrix which has less size. The size, this matrix, less the size of initial matrix on the 1. And after them, we can repeat the previous operation and reduce this matrix to the matrix of the less size. And step by step, we obtain the matrix which has either 1 rows or 1 column. And for this matrix, this matrix has the echelon form. The matrix has echelon form. If we obtain the matrix in the echelon form, we can apply the same method to obtain the solution of this matrix. The idea is the following. Have the same idea. First of all, I illustrate this idea on the some partial case. Let me have only three rows. This element is equal 1, this element is equal 1, and this element is equal 1. And we have reduced echelon form in this partial case. And our aim transform the matrix which consists the element with consists the leading element into identical matrix. In our case, the 3 first column contains the leading element, and our goal to transform this matrix into identical matrix. How to do this? We can use the elementary operation and transform the element which lies upper than leading element in the last marked column into 0. We doing the same operation in the previous case, but in the inverse order. We obtain on this place the 0, and for these rows we use the same operation but in the inverse order. We put the R2 is equal R2 plus minus I23 times R3. R1 is put R1 plus minus A13 times R3. After this operation, we obtain on this place 0 and on this place 0. Do you understand? Yes. And after this operation, we obtain the following matrix. And after that, we obtain the matrix which has the less size than previous matrix, and we repeat this operation for this matrix. After finite steps, we obtain the identical matrix. From the matrix which formed by the distinguished column which contains the leading element. And we have two parts to apply our method to solve the linear system. First part, to obtain the row echelon form matrix, and for this we are using the Gaussian elimination method. The step 2, to obtain from row echelon form the solution form for our matrix. We consider the collect of columns which contains the leading element, and this matrix is the square matrix, and using the Gaussian elimination method, we transform this matrix into identical matrix using Gaussian elimination method, but in the inverse order. We subtract the last rows from previous rows to obtain 0 in the last column of our distinguished matrix. We subtract the last column which multiply on the corresponding element, such that to obtain 0 in this column which lies up the leading element. And after this operation, we obtain the matrix which has the less size than initial matrix. And we obtain on these places 0. And we obtain the matrix which has the less size than previous, and we repeat this procedure, and step by step we obtain the identical matrix in the place of the distinguished square matrix. Example. Let's consider the following example. . First of all, we have such matrix. The augmented matrix has the following form. The first operation, our goal to put on these places the zeros on these places. R2 plus minus 1 R1, R3 plus minus 1 R1. And in this place we obtain 1, 1 minus 1, 1. 0 minus 2 plus 2 1 0 minus 2 0 0. Do you understand? Let's multiply second row minus 1/2 R3 we can change the places of these two rows. It's not I would like the identical matrix, but in this case I obtain the matrix not identical, which matrix like the identical, but two columns changed places. But if I change the place of last two rows, I obtain exactly identical matrix. The following operation, our goal to obtain on this place is 0, and I subtract from last rows, previous rows, and I obtain the following matrix. I can change the sign in these rows to multiply the last rows multiply on -1. I change, and I obtain reduced row echelon form. And from this echelon form, I can obtain the solution. I need only one step to obtain the 0 on this place. I can add to the first row the last row, and after this operation, R1 is equal R1 plus R3. In this place we have 0, and we no need in the step which transform this element in 0, because this element is equal 0. And after applying this operation, we obtain we obtain 0, the ratio 1, 2, 1, 1. And last step to obtain on this place 0. And you can apply the first operation. We subtract from the first row second row. And we obtain the solution form for our matrix. X1 is equal the ratio 1, 2, X2 is equal 0, X3 is equal minus the ratio 1, 2, 1, 2. We can identical matrix in the left side and the solution. But this identical matrix forms only distinguished columns which correspond, which are defined by a leading element. We consider the leading element, and the column which contains this leading element contains some square matrix, and our goal to transform this matrix into an identical matrix. In this case, we have more long rows, and at the end we can obtain not square matrix. But in this matrix, the column which contains the leading element forms identical matrix. Maybe any question? Okay, thank you.